this video, we want to talk about, I guess, the simplest problem in quantum mechanics, where we have a non-relativistic particle of mass m, so in one dimension, which is confined in a potential that vanishes from minus a to a. Okay, so the problem is to find the energy values of the states and corresponding normalized wave functions. So that's the first problem. And the second problem is to find, so if you have a particle with a wave function proportional to a squared minus x squared, what is the probability that the particle will be found in the state of the lowest energy? So that's what we have to find. Okay, let's start. As we have from our problem, the potential can be written as, let's take v of x. So it is 0 if x is between minus a and a, and it is infinity if x is somewhere else. Now, we also have boundary conditions. So those boundary conditions are written here. So the function become infinity at x equals minus a and plus a. So the wave function must vanish at x equals plus a and minus a, and that is psi of minus a is 0 and psi of a is 0. So the question is to find energy values and normalized wave functions. And so inside, so a small sketch of the potential would be, here is v of x, here is x, here is minus a. So these are the walls, and whatever the wave function does, it's supposed to be like so, or better say, let's say like this. So it starts here and it ends here. So I'm just drawing here, but actually this point should be here. So everything should start at minus a and end at minus a. Okay, now everything what you do here, it's starting from Schrödinger's equations, which for v equals 0, it is minus h bar squared over 2m d squared psi dx squared e psi of x. And let me just go back one more time here. Just remember, so the wave function starts here and ends here. So every wave function, whatever down it in here. Now one can write this d psi x over dx squared plus k squared psi equals to 0, where k squared is equals to 2m e over h bar squared. And I guess most of you have seen this equation. This can be seen also in classical mechanics course. So, and the solution is straightforward. We can write a general solution of psi as psi of x, a times sine kx plus b times cosine of kx. And here is where we use those boundary conditions. So we know that psi of minus I is a times sine of minus k times a plus b times cosine minus k times a, which is supposed to be 0, and psi of a is big A sine k times a plus b times cosine k times a, which is again 0. And once you solve those two, you get b equals to 0 and 2a times sine ka equals to 0. And from this, we can write that k times a should have the values of n times pi for n equals 1, 2, 3, and so on. So now we have the equation for k, which is k equals n times pi over a. And we also have an equation for k squared, which is 2 times m times e h bar squared. So now we can substitute here the equation for k and get an equation for energy, which is h bar squared over 2m times n squared pi squared over a squared. This is the equation for energy. So this is energy values of the state. So when you're on first state, second state, that tells you, so n equals 1, n equals 2, n equals 3, and so on. Now, for the wave function, as we know, we have b equals to 0. And now a general form of wave function can be written as an times sine, and for k we have this equation here, which is n pi over a times x. So this is the wave equation, but of course we need to find the normalization constants, and this is done through the normalization condition, which is minus a plus a, so the integral of this wave function squared times dx is equal to 1, which is an squared minus a plus a sine squared of n pi over a times x equals to 1. And here it's a small exercise where you need to check that this integral is equal to a. And you have a n squared, a times 1, from which we get a n is 1 over square root of a. Therefore, a final a finite version of normalized wave function will be written as psi n of x 1 over square root of a times sine n pi over a times x with energy values for the states psi bar squared over 2m n squared pi squared over a squared for n equals 1, 2, 3, and so on. So this concludes the first part. So this is the first part where you find the normalized wave functions and energy levels. Okay. Now it's the second part of equation where you have, now suppose that a particle, you have that particle, it's placed on a state that the wave function it's somehow proportional to a squared minus x squared. Now we need to find what is the probability that particle will be found in the lowest energy state. Now it says here that you have a wave function that is proportional to a squared minus x squared. So mathematically that means that you have a psi of x that is proportional to a function. So okay, let's say it like this. Is proportional to a squared minus x squared. But as any other wave function, we need to normalize it, and we write it as a c times a squared minus x squared. So we need to find this c. And again, using normalization conditions, you write minus a plus a c a squared minus x squared all squared equal to 1. And so you need, again, one more step. Let's say c squared minus a plus a. You have a squared minus x squared. This is all squared. C squared. Okay, this is equals to 1, and I guess this is quite trivial integral, but from which you get c equals to square root 15 over 16 a to the 5. And now this function, this wave function psi of x is square root of 15 over 16 a to the power 5 times a squared minus x squared. Okay, good. Now the next step is to find the probability. Now, so the probability of finding a system in the ground state psi of 1, so a ground state, is psi 1 of x from Cn of x. So you put n equals to 1, so basically you put n equals to 1 here. And the probability, let's call P, is given by C1C. Remind you, sometimes I call it psi, sometimes C, so yeah. So this is the probability of finding the system in the ground state psi 1. And the psi 1 in our case would be here. So from here you get psi 1 of x 1 over square root of a times sine. So n is 1. You have pi over a times x. So this is the ground state. Normalized wave function for the ground state. Now we just need to multiply those two functions and find that probability is so minus infinity plus, so minus a plus a, 1 over square root of a times sine bx over a times square root of 15 over 16a, a squared minus x squared dx squared. And well, you find that the probability is somehow 0, so it's another way of another test for viewers to see if I got this right or not. So you have a 0 probability of finding that particular case. So now what is the interpretation of it? The interpretation is that the ground state wave function, so we can write the ground state wave function psi1 of x is proportional to sine pi x over a, which is an odd function, and basically this is anti-symmetric. About the center at x equals to 0. So what it means that psi1 of minus x is minus psi1 of x. While psi of x is proportional to a squared minus x squared, which is even function. So you have psi of minus x is equal to psi of x. And what does this mean? So this psi1 psi, so the question is, what is this thing doing? So we can, okay, let's write it like this, like what is psi1 psi doing? Maybe a good way to put this would be like, it is like measuring how much of the shape of psi overlaps with the shape of psi1. But the problem is that when you try to project an even function onto an odd function, so in this interval minus a plus a, you see that you get always 0 because they are orthogonal to each other, and once they are orthogonal to each other, the overlap the overlap it's going to be 0. So that's why you have this this probability here 0. Okay, so this is the end of the problem, and I guess this is one of the simplest problems in quantum mechanics course. So this would be first chapter problem when you learn about states and wave function and so on. Okay, thank you for watching.